What if I told you an AI learned to see by reading not a million labeled photos, just the internet? Nobody taught it what a dog looks like. It just read enough captions next to enough photos and figured it out alone. This one paper is the reason Stable Diffusion understands you. 400 million image and text pairs, that's the entire training set, and nobody sat down and labeled a single one of them. The team just scrapped pairs of pictures and the words already sitting next to them online. No fixed categories, just whatever the internet had already written. Before this paper, every serious computer vision model had the same limitation. You picked your categories ahead of time. You trained on those categories, and that was it. A model trained on the 1,000 ImageNet classes can recognize exactly 1,000 things. Show it something outside the list, and it just doesn't have a slot for it. And expanding the list isn't cheap. Every new concept means new labeled data, which means more annotators, more time, more money. The output is locked to whatever categories someone decided on before training even started. Years of compute went into models that still only know a few thousand words for what they are looking at. Move that changes everything. Instead of predicting a category, train the model to predict which caption goes with which image. That's it. That one shift means the vocabulary is no longer fixed by a list. It's whatever language can describe, which is basically unlimited. The setup itself is pretty simple once you see it. There's an image encoder, either a ResNet or a vision transformer, and there's a text encoder or transformer that reads captions. Both of them get trained at the same time and both get pushed into the same shared space where a picture and a sentence can actually be compared. Here's the actual training trick. Take a batch of, say, a few hundred images and a few hundred captions. Out of every possible pairing between them, only the matching ones are correct. The model's whole job is to pull the right pairs closer together in that shared space and push every wrong pairs apart. This is the original diagram from the paper, and once it clicks, the rest of the architecture makes a lot more sense. Mechanically, every step comes down to three things happening at once. Maximize the similarity between an image and its real caption. Minimize the similarity between that same image and every wrong caption sitting in the batch. And apply that symmetrically from the image side and from the text side. No, neither one gets to cheat. And what's kind of wild is the author just published the whole thing as a pseudocode in the paper. Two encoders, two linear projections, one similarity matrix, one symmetric laws. That's generally the entire training loop. No hidden complexity, no secret sauce buried in an appendix somewhere. The dataset behind all of this is called WIT, short for Web Image Text. 400 million pairs pulled using about 500,000 search queries, so the topics they brought instead of collapsing into whatever's most common online. And they kept it at 20,000 pairs per query. Just one vital topic couldn't dominate the whole thing. This obviously wasn't cheap to train. 8 different models total, 5 ResNets, and 3 vision transformers, spanning almost 2 orders of magnitude in compute. The biggest one took 18 days on nearly 600 V100 GPUs, and that's just for one model. What you end up with after all that training is a shared map where pictures and words actually live together. A photo of a dog and the sentence a photo of a dog land near each other in the space, even though the model never saw that exact image or that exact sentence during training. It just learned the general shape of what dog means. So how do you actually use this for a brand new task? First, take every possible class name, say cat, dog, plane. Turn each one into a sentence like a photo of, then the label, and run it through the text encoder. Then encode your new image and compare it against every one of those label sentences using cosine similarity. Whichever one is closest wins, and the model was never trained on these specific tasks. It's just reusing what it already knows. Here's a detail I really like. Most of the captions Clip trained on are full sentences, not single words, so just wrapping a bare label inside the sentence template closes that gap. Adding a photo of in front of the label bumped ImageNet accuracy by over a point on its own, and combining that with ensembling across 80 different prompt variations added another 5%. Free performance basically just from praising things better. The headline research is kind of absurd. Zero-shot clip without ever training on ImageNet labels matched the accuracy of the original ResNet 50 that was trained specifically on those 1.28 million images. Across 27 different data sets, it actually beat a fully supervised classifier on 16 of them, including a 28.9-point jump on Stanford course. There's also this robustness bonus nobody really expected going in. Normal ImageNet models fall apart when you test them on sketches or stylized renditions or photos that just look a little different. Zero-shot clip barely flinches. It closes that robustness gap by up to 75%, and you can actually see it on the same banana photographed 6 completely different ways. And like a lot of these large-scale systems, performance scales in a really predictable way across a 44 times range of compute. Spanning 5 different resonance sizes, the error rate falls in basically a straight line on a log scale. It's the same scaling pattern you see in large language models, just showing up in vision this time. It's not magic though, and the paper is honest about where it falls apart. Fine-grained stuff like telling apart car models or flower species. It underperforms specialist models by 10 points or more. Counting objects in scene, basically random guessing, and on handwritten digits. The classic MNIST dataset, it only hits 88%, worse than a simple logistic regression on raw pixels. Genuinely surprising for a model this capable everywhere else. And there's a more serious limitation worth sitting with. The training data is just unfiltered internet text and images. Nobody curated it for fairness. The paper documents this directly. When Clip labels photos of people, the words it associates with women and men skew toward pretty different, stereotyped vocabulary. That's the model's own released chart, not something critics dug up afterward. As to why you probably already heard of this paper without realizing it. DALL-E uses clip to judge how well a generated image actually matches its prompt. Stable Diffusion encodes every single prompt through a clip text encoder to steer the whole image generation process. And most modern systems that can look at an image and answer questions about it trace their lineage back to the same idea. So zoom out for a second. This paper isn't really about beating a benchmark. It's proof that the same recipe behind GPT, learned from raw, messy, unstructured text at a massive scale, works for vision too. Language became the universal label. That idea is basically the foundation under most of the multimodal AI you're using right now. So here's the whole idea in one line. You do not need perfect labels, you need language and enough of it. That's clip. That's the whole trick.